Hi everyone, thank you all for coming on this last day of the conference in the afternoon. My name is Jannik, I'm from Shutter Network.
I'm Mark from Nethermind.
Yeah, and we're doing a workshop today on Shutterized Gnosis chain, which is very timely because we just launched it, the protocol on testnet on Chiado, which is the Gnosis testnet, during this conference 2 days ago. And yeah, if you like, during the workshop, we can later send your first Shutterized transaction on the testnet. But first, I'm going to give, or we're going to give like an introduction in the protocol, how it works, what we're building exactly, and why we're building it. And in the end, I'm not sure if there's validators here on Gnosis chain, but we're also showing you how you can, if you're a validator, how you can support the protocol and help it work, help make it work. Yeah, so Shutterized Gnosis chain is a collaborative effort. There's many projects involved. Of course, Gnosis chain first and foremost, but also Shutter Network, our side, and Nethermind from the Nethermind client, which is the main client on Gnosis chain. The problem that we're trying to solve, one of it is front running. So that's a problem that's possible in most blockchains today. It works like this. If you're Alice and you want to buy something, you send a transaction to Uniswap, for example. The problem is you publish it first for everyone to see in a public mempool, and then everyone else can react to that, and they can use this information. And for example, Bob, if Bob is evil, they can buy before you and then sell after you. So they can wrap your transaction with two other transactions, and by doing so, they can make a profit. Because if they know that you will buy after them, then the price will increase. So they buy at a cheaper price, and then they sell at a higher price. So they make a profit, which is risk-free, and Alice makes a loss. So it's bad for Alice. And yeah, this is one of the, in my opinion, or in our opinion, one of the most significant limitations of blockchains today. That they allow this kind of behavior. For the most part, blockchains work quite well for users, but not in this case. Another aspect of this is, for the same reason basically, because transactions become public before they get included, this also allows censorship. So a validator or a block proposer who sees your transaction, they can decide, I don't like this transaction, and don't include it in a block. Fortunately, most blockchains, and in particular Gnosis chain actually, they have many validators. So if one validator censors you, the next validator or the one after that can include it. So it won't be. It doesn't mean that your transaction will never be included, but it might take some time. So it will delay. This sort of attack will delay the inclusion of your transaction. And of course, this also has bad side effects because usually, first of all, it degrades UX, but it also might mean that you miss out on some opportunities that you had. So timely execution is important. And of course, this problem maybe today is not as big, but it can get worse if regulatory pressure, for example, increases or other reasons why users might or validators might not include transactions if those increase as well. Yeah, so that's basically what we're trying to fix. And I already hinted at it. The problem is that transactions become public too soon. They can become public before they get included in a block. And we solve this by using an encrypted mempool. So we make the transaction, we hide the transaction by encrypting it. The validator then only sees that there is a transaction, but they don't see what the transaction does, who sent it, and so on. And this means effectively, Bob is prevented from front-running you or censoring you, not because we restricted his powers. They still have all the options, but they don't have the knowledge anymore to do that effectively.
So just to add to this, the crucial bit is who gets to actually sequence the transactions. So if you're able to sequence the transactions, you can extract MEV, you can front-run. But with Shutter, like when the transactions are sequenced, they're still encrypted. So we first submit to a smart contract where they're sequenced in encrypted form. And then when they're proposed, the proposer just has to follow the order that was determined on the sequence on the encrypted transactions. So that prevents any kind of front running.
Exactly. So now if we have an encrypted transaction in a block, that doesn't help us a lot. We need to execute this transaction, and for that we need to execute it. Kind of the naive way to do that would be to ask the user after they encrypted it, decrypt it now please, send the decryption key to the blockchain, and then you can execute it. Of course, this doesn't work at all. First of all, it would be a very bad user experience because now you have to send two messages to the chain, even though you only did one thing, and you need to wait some time in between, so that's not nice. And it also means that the user can decide to not decrypt the transaction. And then we have a big problem because, first of all, we probably have to wait a long time. So every single user would have the ability to stop the protocol in a way, at least for some period of time. And also, economically, it might be a problem in some exchanges. For example, you can imagine that the user sends two transactions. One is, I want to buy this token, and the other one is, I want to sell this token. And then depending on the price movement, they only decrypt one of those. So they can game a lot of these economic protocols. So this doesn't work at all. So because we can't trust individual users. So Shutter solution is kind of the crypto solution, a typical crypto solution to this problem. If we can't trust one person, let's trust many, many people at the same time. And as long as the majority of those people are honest, the protocol works. And this is called, in cryptography terms, oftentimes a so-called threshold committee. So we have a committee of nodes that generates these keys. And we call these the members of the committee the keepers, because keys, and they keep secrets in a way. And yeah, we have an honesty assumption. As long as two-thirds of those nodes are honest, the protocol is secure. And if they're not, if they decrypt too early, for example, if they collude, then the protocol is not secure anymore. Very similar to a blockchain. If all the validators would collude, you also have a problem. And to make sure that these members are honest, we have like a subjective selection process. We have a DAO, so the Shutter DAO selects these members. They make sure that they come from different backgrounds, maybe some companies, maybe some individuals. And if they have the feeling that some of these members are dishonest, they kick them out. Yes, so this was the general principle how it works. This is a workshop, so if you have any questions, we're happy to answer them. Oh yeah, in the back.
You'll have to excuse me because I am not a technical person. So when you say the Shutter DAO, if the Shutter DAO has a feeling that one of the keepers are dishonest, that they'll force them out. Can you define what you mean by feeling? Like how will the Shutter DAO know if someone's being dishonest?
Yeah, that's a very good question, and it is very difficult to do. The main thing is because there is no objective way to do this. So the keepers, they can just collude secretly, and if they have like this perfect collusion going on and no one leaks information about it, then this is just not possible to detect. So you can't have like objective proof about this sort of stuff. So you need some sort of subjective mechanism to do this. And yeah, then this is just how humans and how communities detect this sort of misbehavior. Maybe there's some messages being leaked. Maybe you see some suspicious on-chain behavior. So, for example, if you see some people getting front-run, then you know something is wrong, and then probably the keeper set is doing something bad. Yeah, but I think the more important strategy here is to make sure that the keeper set is honest in the first place, and so that this simply does not happen, that the honesty assumption is, yeah.
Yeah, I mean, the hope would be that if the keeper set is sufficiently decentralized, then it'll be quite hard to get 2/3 of them to all collude on releasing the keys early.
In an earlier slide, you mentioned that if Alice submits an encrypted transaction, that the encrypted transaction goes first in the block. If there are multiple encrypted transactions in a block, how are they ordered, and does it matter?
So the sequencer can, or the block proposer can still order them however they like, but they don't really have a reason to prefer one transaction over the other. So what effectively it means is that they are executed first come, first serve. So the earlier you send your transaction, the earlier it gets included. But yeah, in the end, what it effectively means is that their transactions are ordered randomly because the senders also don't know about each other, so they just send them independently of each other. So
yeah. So just to add to that, so the important bit is at what time they arrive in the sequencer contract. So it does matter the proposer how they order it. So so the sequencer contract, that's where all the encrypted transactions land. It doesn't really matter what order they're in at that point. But then once the order is defined there, it's important then that the proposer does follow it, because otherwise, if they reordered those transactions, then they could extract MEV, because when the proposer's proposing the block, it's decrypted at that point.
One thing to add about the earlier question, what I forgot to say, there are some fancy cryptographic techniques as well that we might be able to employ in the future. It's not something we do now, but something very interesting for the future, which is something called secret sharing with snitching. So you can have you can make a protocol that works that if there is collusion, then any single member can have cryptographic proof that something happens, and then you can that collusion happened, and then you can have a strong financial incentive for them to snitch and to rat out the other people, basically. So that's also kind of a cryptographic and crypto-economic way to make it even harder.
Sorry, I have another question. I don't want to hog the mic, but so as I understand it, for validators, they opt into validating the Shutterized Gnosis chain. But from the user perspective, how does a user opt in to use the Shutterized Gnosis chain as opposed to Gnosis chain?
Yeah, we will see this further in the next session of the talk, and also then in the end when we actually try it out. Hopefully it works. But in short, they just have to encrypt their transaction locally, or their front end has to encrypt their transaction locally, or they have to use an RPC, a special RPC that does it for them, and then it just happens in the background.
Yeah, so with the encrypting, hopefully that we'll have that all in a nice front end. So essentially, it's just very easy to send a Shuts transaction. It'll do the encryption for you.
All right, then let's go on to the next section, implementation. And to start it off, there's many ways to implement these kinds of protocols, and you can make many different trade-offs. So, and the guiding principles that decided which trade-offs we took are the following. First of all, we did not want to make a hard fork. So we did not want to change the fundamental rules of the protocol, because for Gnosis chain, it's one of the important features, I would say, is that they're compatible with Ethereum, with main chain Ethereum, and we didn't want to change that. Another one is we wanted to minimize complexity. We want to keep the protocol as simple as possible, at least in the beginning, because already that part is not as easy, and we want to reduce risks as much as possible. We wanted to have the best user experience that's possible, that we are able to achieve. And we want to be able to iterate and improve the protocol from that starting point where we are now, basically. Less important is perfection. We don't need full trustlessness in the beginning. We're fine with trusting some of the validators in first place. We're fine with trusting some RPC servers in this first version. In future versions, we won't be fine with that anymore, and we will improve on that. But for now, it makes our job much easier. Yeah. So now we just go through different aspects of the protocol. One of it, keep asset management. Where does the keeper set come from? We have a contract, a simple, normal, standard Ethereum contract that's deployed on Gnosis chain, or for now Chiado, that defines keeper sets in terms of sets of addresses. And each of those sets has an activation block number, which says from which point in time this set is active. If a set is supposed to be replaced, another set is added with a higher activation block number. And then the older set becomes outdated or replaced immediately, or when this block happens. And this keeper set management contract, it has an owner that will be the ShutterDAO that can add these sets in the end. It cannot change sets where they're already there, of course, because it shouldn't be able to change history. That would be strange. I don't want to go into too much detail about how the key generation protocol works, because it's quite complicated and no one likes math formulas on slides, especially not on the last day of a conference. So, but I want to highlight kind of the main ideas, or the main idea. Typically, these distributed key generation protocols, they are expensive in terms of communication overhead, because every member of this set has to communicate with every other member of that set, because every member has some sort of secret, and they need to be able to share it with all others, so that in case they are offline, this secret can be recovered. And that means that we have this quadratic overhead. If there's 4 nodes, like in this example, we have 16 messages. If there's 100 nodes, we have 10,000 messages already, so it scales very poorly. Unfortunately, it's fundamentally necessary that we have this. So therefore, and one more thing, of course, or 2 more things, we want to have our set as large as possible. As Mark said earlier, the larger the set, the more secure the protocol is, because collusion becomes harder. And we have to be quite fast. So we want to be able to create keys for every block, which means on Gnosis chain every 5 seconds. So we can't do this sort of process with, say, 100 members for every slot. So therefore, our protocol works like this, that we run this phase only once. So we have a setup phase, and this setup phase gives key shares for every member, and then it outputs one kind of master key. We call it the Eon key, which is because it's supposed to be valid for a very long time, as long as the keeper set is active. And then for every slot, we are able to generate the decryption keys very quickly by just 1 message per node, which is optimal.
So like, just to talk about how this looks from the user perspective. So this Eon key is essentially the public key. So when I want to encrypt my transaction, I'm going to use this public Eon key. And then the keepers, say like every 5 seconds, they're publishing a new set of decryption keys. And the cryptography is designed such that they can just produce the decryption keys only for the transactions that are going to be included next. And then they'll be repeatedly broadcast every slot just for the new transactions. Yeah, once this key is broadcast, this will happen basically before the keeper set gets active. They know they will become active in maybe tomorrow, so they start generating the key today. Once it's done, they publish that key. And since it's very difficult to verify that key, it looks basically random, the keepers run some sort of voting protocol. So every keeper says, this is the key that we generated, and as soon as enough votes, basically 2/3 of that set are collected, then this key can be accepted as valid and will be used. And this voting protocol is done or implemented, or the outcome of the voting is published to this key broadcast contract, which checks the keeper set manager that the right keepers voted on it. And this is basically where the user would go to fetch that key and encrypt their transaction. So we use this key this contract basically as a billboard where the keys are published. Validators. This is what we're going to do at the end of the workshop, and they have to register. So we don't want to
require validators to do things because that would mean we have a hard fork. So we want to make it optional. Validators are supposed to opt in to these additional duties that they would have if they follow the protocol, namely decrypting and including transactions. And they do this by registering. They sign a message, I want to participate, and then they send this message to the validator registry contract. If they want to deregister, for some reason they decided I don't like this anymore, then they can also send a message to this contract. And then everyone can look at this contract and see which validators are participating, most importantly the keepers. Because the keepers will have to decide for every block, do they publish the keys for them, do they produce the keys or not? And of course they only do this if there is a validator or if the proposer for that slot is registered, because otherwise they would just ignore the key and it would be pointless.
And also, if they were to release the keys at the wrong time for a slot when the validator wasn't registered, then you're essentially making all of those transactions public. So someone else could then include them and extract MEV or do something like that. So it's quite important to only release keys when there's going to be a valid proposer afterwards who's actually going to include them and follow the protocol.
Yeah, so now we had kind of the main management components in a way. Now we can see what happens when we actually send a transaction. Users, as I said, earlier they encrypt their transaction by fetching the key from the Eon key contract. And then they submit it to the so-called sequencer contract. And the sequencer contract now, it's called the sequencer contract because this contract basically does the ordering. So the order in which these encrypted transactions appear in the sequencer contract, this determines the order the encrypted transactions are executed as well. And since the sequencer contract only sees encrypted transactions, we already know that there's no chance to front run or use private knowledge to order them. Now the sequencer contract is observed by both the proposers and the keepers. The keepers do it because they check for every slot which keys they have to produce, which transactions have to be executed, and then they publish the decryption keys for those transactions. The proposers watch that contract because they take the encrypted transaction from there, then they take the transaction from the keepers, and then they decrypt them and include them in the block, at the front of the block, according to the order that the sequencer contract told them to. Invalid transactions, for example, users might encrypt junk, or they might not even have enough money to send the transaction, or they might have chosen a wrong nonce. Those transactions will just be ignored because otherwise you couldn't build a valid block.
And also, I mean, for those transactions that are invalid, the user would still have to pay the initial gas fees to actually get them into the contract. So that would prevent them from just spamming invalid transactions.
Yeah, that's a very important point. You need to pay the fee at the sequencer contract because at this point it's already decided that the transaction will be included, and we need it as a sort of spam prevention. Already mentioned it earlier in response to the question we had. Ideally, you encrypt your transaction locally in the front end or in the wallet. You should do it yourself because only this way you ensure that only you know what your transaction does. But we want to, first of all, we want to have a good UX and we want to have it as soon as possible. We don't want to wait for front ends and for wallets to integrate or support this sort of protocol. So in the meantime, until we have this support, we implemented the encrypting RPC server. The encrypting RPC server is a very simple RPC server. It does what a normal RPC server does. But instead of sending, when it receives, you as a user send your transaction in plain text to that server, and then this server will handle that encryption and sending it to the sequencer contract. This means you have to trust this server. They could front run you. But if you do that, then you have like a very good user experience. Basically, nothing changes for you. You only have to change your RPC server, and everything just works as normal. And this is what we're going to try after this, during the workshop part. Questions so far about the implementation?
Perhaps you'll cover that later, but do you have any incentives in mind for validators to come in and register as is?
Yes, so not at the moment. At the moment, we try to keep it as simple as possible. So we built the simplest protocol imaginable. So at the moment, it's just, there's no incentive at the moment, except for kind of something intangible, like you want to support the protocol. You have some sort of incentive because you get free transactions, basically. Validators want to have as many transactions to include in their blocks as possible, and this adds kind of an additional path for them. If they wouldn't do it, then these transactions are off limits for them. So that's kind of a small incentive. And we could imagine that in the future there's like token incentives, or they get like special rights in the DAO or something like that. Yeah, but nothing concrete yet.
Thanks.
What would this mean to hardware requirements? And second question would be, who will be running the RPC servers?
Do you want to say something about hardware requirements?
Yeah, so there isn't any, certainly for the validator side, there isn't really any additional hardware requirements on top of just running a normal Nethermind validator.
I think running the node is already kind of way more difficult than adding this shutter functionality. Who will run the encrypting RPC server? Anyone can run it. It's open source software. I think for now, for the testnet, we run it like from Shutter. In the future, hopefully, we hope that we can convince like the main RPC providers on Gnosis chain to either make it the default or add like a variant of theirs to do that. And you can, like I said, you can run it yourself in theory. That might actually be a practical option if you don't want to change your wallet or your front end. You can run it locally, and then you again don't have to trust anyone. I think there was a question.
Simple question. I'm just wondering if the sequencer contract is doing any specific sequencing of the transactions, or it's just first come, first served, and if changing the sequencing in the contract could have any other impact on the rest of the system.
So at the moment, there's no complicated rules. It's just first come, first serve, which essentially means that the block proposer who included the encrypted transaction can decide it. You could imagine that you could come up with more complicated rules. For example, you could do some sorting by gas price, or you could do some auction system in that contract to change the order. I think there's like, it's actually a very interesting design space because it allows the protocol itself to determine the order of transactions, which is not being done right now. But yeah, for now we don't have any specific rules for that. And to be honest, I think in practice, first come, first serve is kind of the close to the best solution anyway, so I don't think we will do anything fancy there.
Okay. And you mentioned you could sort by gas price. Does that mean that there are certain parts of the transaction that are not encrypted at that point?
So, I mean, yeah, so as it is, you wouldn't be able to do that. Like, potentially using some kind of like crazy cryptography is possible to do this kind of sorting on encrypted transactions. Where you just reveal like certain, or yeah, you can still order them without necessarily like with them still being fully encrypted. But this is like more theoretical at this point.
Okay, all right, thank you.
Also, the transaction itself is fully encrypted, and you can't get anything from there. But kind of the submission transaction, the transaction that calls the sequencer contract, that of course is public fields. And this transaction, as we mentioned earlier, it has to pay the transaction fee in advance. And this is done by a kind of a value transfer. So in a way, there's a gas price in there implicitly.
Is it possible encrypted transaction to be leaked in case of chain reorg?
Yeah, that's a very good point. This protocol is in general not reorg resistant. So if you are able to reorg the encrypted transactions while already knowing the decryption key, then there's no protection against this. Two solutions in the future potentially. One is, I forgot, a single slot finality. That's kind of very easy for us to say because other people would have to do the work, but that's ideally we would have that, and then the problem is just solved. The second one is also not a perfect solution, but we might be able to make transactions or at least messages that are only executable in a particular slot, and this or before a particular slot, and this would prevent most reorg attacks because even if you're able to induce a reorg, usually you can only propose blocks in the future, so you can't, and then this transaction would just not be executable anymore.
Using just the public fields that you referred to before, could you imagine a scenario where an adversarial validator could heuristically sequence transactions and still potentially extract some MEV? Or would that be completely infeasible?
I think in practice, no. I think in practice, it's the transaction is encrypted, so there's no information leakage, at least in theory. You could imagine that. So this becomes very complicated, and the question is, you can probably do it, or potentially do it statistically, and then the question is, can you do it efficiently? So is the value you can extract more than the transaction fees you pay on average? There's probably some scenarios you can imagine. One is if you know, I don't know, if you see on Twitter that a new meme coin is rising, and then you probably can guess that most of the transactions, or that, and there's like lots of transactions, then maybe you can guess that many of these transactions buy this meme coin. But then the question is, do you actually react to information that's in the transaction? I don't think so. I'm not sure if I would call that front running anymore.
Yeah, I mean, there's quite a lot of information that's potentially leaked. So, like, you have to, as Jannik said, pay the transaction fee up front. So you have that. You have the address that sent the transaction, like the size of the transaction, the time, maybe the IP address. So you could definitely take more steps to obscure more of these things. But I mean, hopefully, it's kind of hiding enough that it would prevent a lot of the worst kind of front running and stuff. And then this is like other areas that we can look into and develop further.
Well, actually, we have to sort of spoof high-value transactions if you're a high-value user.
Yeah, you can probably, like for example, you can make the arbitrarily increase the size just to hide the size. That's something you could do. You can use a different transaction or different address to send the encrypted transactions to the actual execution. That's another way to hide information. Yeah.
You could also use Tor and like to hide the time as well. Like if you send lots of sort of like dummy transactions, I guess in a way you're wasting money, but then you can't tell the time because you don't know what's a real transaction and what's not.
What's the key size for the encryption that's used? Is it somehow kind of determined by the user? Because it has some impact on the gas, right? Because the bigger the key size, the bigger the payload that needs to be stored in the smart contract.
So we only publish the encryption key, like this EON key, and we only do it once, so once per keeper set. So this is not going to be done very often. The decryption keys are actually never on-chain. The transactions are decrypted off-chain, and then only the decrypted transaction is sent on-chain. Okay, so the size of the key doesn't add any overhead. The encryption itself, of course, adds overhead. First of all, the transaction ends up in the state twice, once in encrypted form and once decrypted. So there's some overhead. and we have to add some padding, and kind of the encryption itself has a constant overhead as well.
Okay, thanks.
Okay, if there's no more questions right now, we can maybe take a look into the future. There's, as I said, a few points where the transactions where the protocol is not perfectly secure. One is that we have a lot of trust in the individual validator. If they decide to ignore the order that the protocol tells them to include transactions, nothing happens at the moment for them. So to make this more safe, in the future we can implement slashing conditions. We can require them to deposit some tokens, and then slash these tokens if they produce an invalid block. If we are able to make protocol changes in the future, then we might even be able to make these blocks simply invalid, and then those blocks would be ignored by the network. That would, of course, be the ideal solution. And also, at the moment, it's opt-in. We require validators to opt in. At some point, maybe we can make it mandatory that they don't have a chance. They always have to follow these rules. At the moment, if the rate or the fraction of registered validators determines kind of how long you have to wait for your transaction to be executed. If all transactions, if all validators are registered, then transactions will be executed in the next block. If it's only half of them, you have to wait. Depending, 2 blocks on average. So this is something we can do on the validator side. On the keeper side, we can also require staking. We don't have that at the moment, but probably we'll have that very soon. We can have social slashing. This is what we talked about earlier. If there's kind of reasonable conviction that a keeper cheated, then we can socially slash their deposit. And potentially, also something I mentioned earlier, we can have fancy crypto that makes collusion much harder, and we can have this snitching feature. Yeah, so this is the end of the presentation. We have 22 minutes and 35 seconds left. That's plenty of time to send some encrypted transactions, and then in the end we also want to do this, or show you at least how the validator registration works. You can maybe follow along. We can show on the stage how the process works, how you can register. We have like this small README file that describes what you can do. You can scan the QR code or enter this URL. Maybe you can make it a little bit bigger. tinyurl.com/ytjm6mbw. And what we have to do is, first of all, just add this encrypting RPC server. I didn't think this through. Now I can't scroll without you having to maybe I can open a new window. Okay. So I guess most people are very familiar with crypto and all the lots of the things you have to do there. You probably have already added an RPC in your crypto life. We now have to add this encrypting RPC server. We use MetaMask in this demo. We click on Network, Add Network. Then we go to the very bottom, add a new network manually. We enter the network name, Shutterized Chiado, new RPC URL, this one. Oops. The chain ID 10200, that's just the Chiado chain ID. Currency symbol XDAI, and the block explorer, block scout. We save, we switch to that network, and now whenever we send a transaction, it will be encrypted. So let's try that and hope that it works. We click send. We can just send to ourselves 0.01 xDai and confirm. So now we have at the moment about 1,000 registered validators. There are about 6,000 validators on Chiado right now. So at the moment it will take 6 blocks on average, if my math isn't wrong. So it might take, much quicker. We got lucky. So the transaction was actually confirmed. Yeah, we can look into the sequencer contract. There we will see a bunch of transactions, and one transaction that was sent 32 seconds ago. This is the transaction that the sequencer contract, that the encrypting RPC server sent to the sequencer contract. We don't see a lot of information there because it's encrypted. So we don't even see that we sent this. But we see if we click on, we can of course check the MetaMask confirmation. We can view it on a block explorer and see that the transaction is what we expected, what it was, a transaction from us to us, 0.01 xDai. Yeah, so this is how it works.
So there are like 2 transactions there. So the first one, when it was sequence encrypted, and then this one, we had to wait a little bit until the proposer included it in its decrypted form.
Maybe we can try it again and we get unlucky this time. Maybe it takes longer. Can do the same thing. Confirm. We see the transaction from the encrypting RPC server is pending right now. It was just sent here. It should get included in the next block. Was included. And we're still waiting for the next participating validator to be in charge of producing a block.
Yeah, so it's just pretty random like as to when the validator gets selected, and if it happens to be running Shutter. So it could be like, it's average 30 seconds at the moment, but could be like potentially longer.
And that's why we need lots of validators to participate. Does it work? Did anyone try? Can we help? Oh, yeah. I forgot about this. I wanted to add a link to the faucet. Now our transaction was confirmed.
How many blocks did it take?
Good question. Does it say included? This one was included in block 94, and the sequencer transaction was included in 81. So 14 blocks. So a bit unlucky. Twice as long as it should have been.
Pays for a sequencer transaction right now?
Sorry?
Who pays for the sequencer transaction using the RPC?
Yeah, at the moment it's the encrypting RPC server. So you get free block space if you use it. You still have to pay the transaction fee for the actual execution in the end, though. In the future, transaction fees on Gnosis are relatively cheap, so it's possible that this will run for a while. But we could imagine that you have to prepay some amount, and then you get like a certain amount that you can spend.
So you could already consider this as part of the gas estimation call response from the RPC.
Ideally, yes, but that would probably require a wallet integration, basically.
Yeah, I mean, ideally we'd have the front end, so you'd just be paying for it yourself. Yeah, yeah. So you can just pay for it with your own wallet, or people can run their own RPC servers as well. Maybe I could just quickly talk through how you go about registering a validator.
1 second. Did someone send a transaction? Because I see a transaction in the sequencer contract. Yes. Awesome. Thanks. Let us know if it works, because we won't get any confirmation, because we only see the encrypted transaction, so we won't even know which transaction yours is. All right, maybe you can.
Yeah.
Are there any Gnosis chain validators here, just out of interest? Many. Awesome. So, I mean, for now it's just Chiado, but hopefully we will be on mainnet soon. So then, this is for you, hopefully.
Okay. Yeah. So to register your validator should be like pretty similar to like normally registering a validator with a couple of extra steps. So one thing you'll have to do is change your execution client to use the Shutter version of Nethermind. I guess in future we'll merge this into main, so you won't even have to do that. And then you have to generate your validator signing keys in the normal way using the generator tool. And we're going to need to use these to sign the Shutter messages to prove that it's you who's registering a validator. So another step you have to do is creating a burner address, or just like any address that you're happy to just put in a bit of XDAI just to actually submit these transactions on chain. Just set up all these parameters here. So you just need the beacon node endpoint, put in some information about your burner address and the path to your key store files. And then you can just sign and submit the transactions. So I already have my config set up. So I'll just quickly demonstrate what it looks like. So I'm just going to run this script, which is going to sign the transactions. So yeah, it gets all of the information from the beacon chain about the validator and loads the key stores, and then it generates this bunch of bytes, which is the Shutter registration message, and then it signs it using the validator's keys. And then I just have to run the other script. And then this is just taking the previous signed message, and it's going to use the burner address to send on-chain, and then that's just the receipt. So I guess may as well show this in the Block Explorer.
Giado, probably.
Oh, yeah. Okay, yeah, here we go. So this is an asset. So the validator is registered, as easy as that. Okay.
You're running like 50 validators. Do you do this for each validator? You can do it.
Yeah, so in the key store files, when you generate them, it will generate all of them, and the scripts will just run through all of them and sign and submit. So for one, it's very quick, but it can actually take a while for if you have a few hundred or something to sign all of these messages and submit them.
We could potentially have like an aggregated signature, something like that, to make it easier, but for now, we just wanted to keep things simple, and it's only a one-time thing you have to do. So we didn't think
But
it.
it's automated and you don't have to do it 50 times or 100 times.
Yeah, no, the script just goes through and does it all for you.
All right. I see many calls to the sequencer contract. I hope all of them go through. As I said, we can't confirm them because of, it's difficult to see them because of encryption. If not, please let us know. It's a testnet, so things are expected to break. That's a question.
I have a question. So when I submit a transaction, it triggers multiple transactions, right, on the sequencer? Is that normal behavior, and just to understand?
No, if you send a transaction, it should be converted into one transaction in the sequencer contract. But maybe many people did it right now at the same time, so maybe you see those transactions as well there.
Okay.
I hope so. We actually had a bug this week that we had one transaction which resulted in lots of things. I think we fixed it. Maybe, yeah, but it should ideally only be one transaction. Yeah.
Okay.
I'm just interested to know a bit more about how you pay for the transaction. So you said that when you submit your initial transaction includes the encrypted transaction, you make a payment at that point to cover the cost of the encrypted transaction. Could you just go into the details of how that works? And I'm guessing that you might need some new UI elements at the wallet level to enable setting that new price. And I guess that right now the RPC encrypted server is handling that for you, but could you just go a bit deeper?
Exactly what you said, basically. So at the moment, the the encrypting RPC server pays a fee when they send the transaction to the sequencer contract. They do that by a simple value transfer. So the sequencer contract is payable, and they have like a minimum amount that
So I mean, it sets essentially like you have to set a limit on how much it's going to cost, and then you pay up front the whole cost, and then if it exceeds that amount, then it just won't be included.
And if it's less than that amount, do you get the money back?
At the moment, no. At the moment, you pay double, basically, or at least the sequencer, the encrypting RPC server pays, and it doesn't get refunded. This is because mostly because we can't do protocol changes. If we could do protocol changes, we could make it much nicer that you only pay in advance, and then you execute a decrypted transaction. Then this wouldn't pay anymore at all, and maybe the remainder would even be refunded. This we do so Shutter Network is we're also implementing it on OP Stack. There we're able to do protocol changes. There you get a refund. In Optimism right now, this is not possible. We could imagine that you can do fancy things, like do afterwards like a zero knowledge proof. You had this transaction, paid this much, you paid this much in advance, so you get the money back from the sequencer contract. But for now, this is we thought this would be too complicated and not necessary initially, anyways, because Gnosis chain transaction fees are so low, anyways.
And then one more. How are the fees distributed from the sequencer contract to the validator in question that processes the transactions?
At the moment, they're just burned. So the fees in the sequencer contract don't go anywhere. In the future, we could imagine that maybe either the block proposers can withdraw them, or Gnosis DAO can withdraw them.
Okay, cool.
And the validators would still get the tip from when the transaction is actually included as well.
Okay, thanks.
So as I understood, the sequencer contract is kind of a work list for the validators to walk it off, right?
Yep.
So they will go through it and just submit it. So are there any measurements on your side to prevent that one of those items in the contract could be executed twice? I mean, they will probably fail in the second time, but it would most probably create some costs.
So if a transaction
Some kind of walking or synchronization that you make sure that the transaction is not tried to be decrypted and submitted twice.
Yeah, it's normal transactions, so they have a nonce. And if you would include it twice, it wouldn't be executed, or this transaction would just fail. It would be invalid because of a duplicate nonce.
Okay, so there's no extra protection around it. You should just get it rejected by the node afterwards. Once the validator tries to
yeah, exactly. Or actually, the validator checks this before that the transaction is includable. And otherwise, they don't even propose the block like this. They kick it out before that even.
Okay, good, thanks.
All right. If there's no more questions, I think this is the end. Thank you all for coming. And yeah, catch us afterwards if you have any more questions, or tried it out and it didn't work, or tried it out and it did work, because would like to hear about it. And yeah, thanks.